We are on week number 8. So we are just halfway done the semester. All right, so experiment number 6, we're going to take a look Newton's second law. You can download the lab manual and the data sheet. All right, and then let's take a look couple of basic ideas what we're trying to discuss here. Technically, in terms of theory part, we already covered everything, almost every aspect of Newton laws by now. Because of that, you have a good idea about the Newton law and the application of them. So that's what actually we are testing in this lab, okay? Right. So the basic idea of the Newton laws, everybody familiar. So if you have an object, there's 3 laws, and then 3 laws are connected together, right? The law of inertia and the second law, force equal ma, and the third law we actually use in the draw in the free body diagram based on the third law, right? So those 3 laws are connected to each other. That's what we try to investigate, but the calculation is depending only on the second law. So now, for example, this question we done in class in this figure 1. If I have two objects are connected together by a string, if objects are moving, let's say object B go downward direction, object A go in horizontally on the plane. If there's no friction, I can build the two linear equation, this equation number 2 and 3, and then solve them and then figure out tension and acceleration in terms of mass and the gravity, right? So we done that in class setting. So that the exact problem we're gonna investigate by using the experiment. So that's part 1 of this experiment. Since we don't have a setup, what we're gonna do, we're gonna use a simulator to simulate this behavior. So because of that, our result gonna be very accurate. Other than that, the simulator is exactly the same setup as the in-class setting, okay? So that one part of the experiment. And in the second part of the experiment, what we're trying to do is actually trying to understand the mechanical energy. Now, when it comes to the mechanical energy, so the mechanical energies are 2 types. So in generally, mechanical energy, this whole class is actually about mechanical energy. These are 2 types. The object is motion, then we can find the kinetic energy of the object. Object is on rest, however, object is actually above the ground level, that can have a potential energy, right? So those are the mechanical energies. But when it comes to the potential energy, there's 2 types of potential energy, but in this experiment, we're considering only potential energy due to gravity. But in class, we will talk about the potential energy due to elasticity of the object, like the spring, for example, can store potential energy. That we will talk about later, but in this experiment, we are only investigating potential energy due to gravity, okay? That's the part B of this experiment. Part A, just investigating tension and the acceleration of the combined object under no friction. And in the second part of that same information, we're going to use to understand the mechanical energy of this system. That's the plan. Now, when it comes to the mechanical energy, this is the situation, right? So I have a object is actually moving only on horizontal plane, starting from here. Let's say this is time equals 0, initial velocity 0 point, and then let's say point A, object number 1, and then start moving on rightward direction with some acceleration A. After some time, this will reach some other point right here. This is connected with this string, right? So it connected with this string to another object right here. There's a pulley here, and then object number. Let me take a look what I'm using for the masses object 1 or object 2 mass M1. So I'm using this as object 2. Okay, I want to go exactly same variables here. Otherwise, our equation will be a little bit different after we build it. Mechanical energy, and this is actually object number 2. This is 1. Okay. Since this is connected together, if this object number 2 start moving horizontally, this will be time equals 0. This also initially starting with the 0 velocity. And then let's say this is the ground level. And then initially it is starting at h distance above the ground level. This will move downward direction. At the same time, it will drag this object some distance from starting point to here. Okay, this is after some time. This object has a velocity v. Since this is connected together, object number 1 has the same velocity but downward direction at the end. So this is final point, and this is also final point for this one. Now, what we try to understand for the second case, now by using the experiment or the simulator, I can actually find this final velocity. If this is a real in-class experiment, we're going to use the photo gate. By using actually photo gate, by investigating this part of the motion, I can easily find the final velocity. What we're going to do, this is the object number 2. This is time equals 0 point. And this gonna go some about h distance on the horizontal plane, because that's same as this h distance on horizontal plane, and then gain some velocity v, right? If I want to find that one, we can do easily. For example, this is under acceleration. I can use linear equation to figure out the connection between acceleration, velocity, and the height, right? Velocity and the displacement. If you, for example, use delta x is equal v0 t plus half a t square, then the delta x going to be h. This part going to be 0 plus a by 2 to the power t square. So which means simply you can calculate acceleration, for example, just measuring the time, right? So that's one easy way of doing that. That's what exactly we're going to do if this is in class setting. So what we're going to do, we're going to set up a photo gate right here, exactly about like h distance away from the starting point. This is going to be starting point, initial point, and the final point. Then the photo gate can actually tell you the time after it complete. So by knowing time, by knowing distance, how much is travel, I can find the time. And by knowing acceleration here, for example, I can find the final velocity, initial velocity plus a times t. So initial velocity 0, then the velocity going to be just acceleration times the time. All of these actually we can easily find just by measuring the time. Okay, but this part right here, the simulator will do it for you. That's the easy part with the simulator, right? So we don't need to worry about that extracting the time. Simulator will tell you that information. Not only time, it will tell you calculated acceleration, it will tell you calculated final velocity. It will tell you all of this information, okay? So since any questions so far? Okay, since the simulator telling us all those information, now I can take a look in terms of mechanical energy what we have. So let's take a look in terms of mechanical energy. Object is started here, object number 2, and then reach at the end this point. That is final, that is initial. Initial velocity is 0, finally it has some velocity. And on the other hand, object 1 started here, initial point, initial velocity 0. Finally, this is going to reach the ground, okay? It's going to reach the ground. When it reaches the ground point, that's the final point. It has some velocity v. Now let's take a look at the mechanical energy. What's the mechanical energy of this system? So the mechanical energy means kinetic energy plus the potential energy, right? So the mechanical energy is kinetic energy and potential energy, right? So let's take a look mechanical energy at initial point. So let's take a look total mechanical energy of this system at initial point. when it is starting. Then I can write kinetic energy initial plus potential energy initial. Kinetic energy, now you know, we will talk about this equation a little bit later on this Wednesday, probably, how to get that equation, proof of those and everything. Kinetic energy, you know, in generally, equation is half mv squared. Any object moving with velocity v carries the kinetic energy. Potential energy, on the other hand, m times g times the h, right? Whenever the object is above the ground, the amount of work done against the gravity is actually called the potential energy. That also we will take a look on Wednesday, proof of those equation. Okay. Now, in this case, I can say initially both object is at rest. So which means initially there's no kinetic energy, because this is a system now, right? So when I use the term system, so which means system include all the object which actually on that motion, okay? In this case, these two objects are connected together, object number 1 and 2. As a result of that, system include object M1 plus M2, okay? So now what we're considering here, mechanical energy of the whole system. Question. Okay, then initially objects are at rest, so which means there's no mechanical energy. However, object number 1 is actually moving only on horizontally, right? If an object moving only on horizontal plane, that object not actually changing any potential energy itself at all. What we interested here, not the potential energy one particular point, what we interested here, potential energy change between 2 points. Okay, later in chapter number 7 and 8 from this Wednesday and the next week, that's what actually we're going to study. So we're going to take a look all of the question which we discussed earlier by using Newton laws. We're going to reinvestigate all of those questions by using only concept of energy. When we using the concept of energy, every single question, every single object, when it moves from one point to another, always there are going to be an initial point and the final point. What we interested is actually whether some sort of energy change between those 2 points or not. That's what the main concept is. So which means if you take a look object 2, moving only horizontal plane, if there's no vertical change, potential energy for object number 1, we can consider not changing at all. However, object number 2, not changing at all. However, object number 1 is started here, h distance above the ground, and then finally it reaching the ground level. So which means object number 1 definitely going to changing its potential energy. So we can say object number 1 has a potential energy when it is starting mgh, but we can neglect any potential energy of the object number 2 because final point and the initial point are on the same level. Question. Okay, which means the mechanical energy when the system is started, just mgh, okay? And then let's take a look the mechanical energy when at final point. When it reaches the final point, again, I can consider mechanical energy always kinetic energy plus the potential energy, but now it's final point. Kinetic energy, both objects now moving with the velocity v. So which means both object has a half m1 v square plus half m2 v square. That's the kinetic energy. Plus potential energy, object number 1 reach the ground level. Usually, one other thing I forgot earlier to mention that when we first discuss about the potential energy, whenever the object is moving has a kinetic energy, whenever object is relative to ground level is at different location, then that has a potential energy, right? So which means the potential energy is a relative energy. It's not the absolute energy at all, right? That's why when you write the potential energy, you write mgh. The direction of h, how you measure relative to y-axis, can carry the sign, okay? So which means When we talk about potential energy, kinetic energy always absolute value because it mv squared. Since this is v squared, doesn't matter whether v is positive or negative, you will get just an absolute value, just a number. When it comes to the potential energy, we say mgh. So depending on where the h is relative to the initial point is 0, point, okay? Relative to initial your Cartesian coordinate system 0, point, this potential energy can be actually positive or negative, okay? Make sense, following? Which means when the object reach the ground level, it doesn't have any potential energy. Object number 2, on the other hand, doesn't have any potential energy at all. So mechanical energy final going to be just simply half m1 plus m2 v to the power 2. So this is what we're going to check really, because we know this information. M, G constant, H will be known. We can actually measure, or the simulator give that number. V is actually measurable. We just discussed mass M1, M2 same. Now what we're going to check, if mu is 0, mu is friction coefficient, right? Friction coefficient 0 means friction force is actually 0. Friction force we discussed, right? So the friction force means force against the motion. So if there's no any force against the motion, then the motion is actually under energy conservation. So which means if there's no any force to get rid of energy, then there's no energy lost during the motion. So we can just simply say during the object motion, energy is conserved. So which means I can say delta of E must be 0. Delta is total mechanical energy final minus total mechanical energy initial equals 0. So which means I can simply say mechanical energy final must be equal to mechanical energy initial. So that I can test actually by using this experiment. That's the part B of the experiment, okay? All we're going to do just simply calculate energy initial. We're going to calculate total energy initial, and then we're going to calculate total energy final, and then we're going to check whether these two are equal or not. If these two are equal, we know conservation of energy is actually validated. If not, then we have to take a look what is actually the problem with the simulator. If you're doing this in class, we have a setup called the air track, linear air track. Linear air track is actually, I think I mentioned this earlier too. So the linear air track is just simply a solid metal rod inside this hollow. Then we connect this into the compressor. Compressor is actually creating the huge airflow. Then we send the airflow into this solid air track. So this metal track has a small holes, very small hole on top of that, actually everywhere on the top, very small tiny holes, okay? Since this air has a huge pressure, air is starting to coming out. Then if you place a cart, like about maybe 200-gram weight a metal cart, you can actually float that cart. You can float that cart on top of this air track. This separation between about like maybe 0.5 millimeter or less, okay? Now what we can do is actually we can create the system, friction is 0. Assume friction is 0 because there's no any solid metal to metal touch or surface to surface touch. You know the friction appears only surface to surface touch. However, when the cart is moving, this you can see now this is the track and then this is the cart, okay? When the cart is actually moving, there's a small air flow in between the cart and the track. Because of that, this air is actually starting to move. So if you look at it, this bottom surface, you have a cart surface right here, air molecules is actually just underneath. Because of that, when the cart is trying to move, there are going to be small friction between the air flow and the cart. That is still possible. So which means if I assume there's no surface to surface touch, my energy must be conserved this situation, you may not able to see that. Reason, there may be some sort of friction due to airflow that called the fluid friction. So the fluid friction is actually part of your physics 2 class that will be, you will be learning that as a chapter 1 on your PHY 290 class, okay, when you go into that class. So the idea is that even though there's no solid surface to surface connection, there's no solid friction there, but still you have a solid is moving on top of the fluid, then you have actually still little bit of air. You cannot technically get any real working condition like this one with friction is absolutely zero. So because of that, you may get little bit of error here. The simulator include very little bit of friction, but if you do this in class, you will get fairly significant error here. Maybe about like, depending on how you measured, 5% error between the initial and the final energy. So that's the second part of the experiment. Question. Okay, then let's start. These two parts are very simple. After we complete these two parts, then we'll come back and then take a look the last part. Okay, last part, what we're going to do, we're going to include the friction and then revisit the problem. That's all. It's not anything new there. Okay. All right. So let's continue to the simulator then. There should be a link on your lab manual, page number 3, very top of that. You click on that, that will bring you into the simulator page. Okay, now that's the simulator page. All right, and then immediately when you go there, you will see a inclined plane. Right now, our interest is not doing anything with the incline. You can actually get rid of the angle. There's a slider on the bottom of that inclined plane. It says 20 now. Just click and drag all the way to 0. Then you can get rid of the inclined angle. We are not doing the inclined problem at this point. And now you have seen this blue color object is our object number 2 moving on horizontal plane. There's a red object which is connected with the blue one with the string, and then which is moving vertically. And you guys know when these two are moving, the tension everywhere on the cable same, acceleration is same on the both object but two different direction. We can calculate those two by just solving those two equation, which is built by using F equal ma, right? So that's the idea. If I can analyze that, then I can validate Newton's second law by using an experiment. Okay, that's the plan. Okay, now let's see a couple of other information. You can see object number 2, mass set it into 10 kilogram. I would leave it like that. Nothing much to worry. It's heavy. If it is in class setting, it's going to be very lighter object, but that's okay. Just leave it like that. And then mass of the object number 2 is 7.5. That's too heavy. We don't need that heavy mass to drag this because the friction is 0. You don't need a lot of force if there's no friction between the object and the surface. You just need very small force to move the object. Okay. Friction coefficient right now setting to 0.14. You have to click and drag and then change that into 0, because we do in the first two parts, part A and part B, with no friction. Now the simulator is set up. Then you can click on the top right here, right hand side, very top. You will see two places you can click. One says show numerical values. Click on that. That will give you the information. For example, what is the acceleration on the system, tension on the string, time it took to go from one point to another, velocity, and how height object number 1 above the ground. Those are the information we need to actually validate the Newton laws. So after we run the simulator, that will give you those information. Only disadvantage is that our calculated value with the masses gonna be perfectly or almost close to perfectly match with the given values with the simulator. Reason the simulator does the same kind of calculation internally, right? So that's the problem. So otherwise, if you do the same experiment, we can do exactly same way in class setting. If you do in class setting, you will get a fairly considerable error on this particular experiment. So that is a good one good thing actually. Getting the error is good. Then you have to investigate what's the reasons for those errors. That actually part of the game. When you become engineer, you can't just assume every single problem you're gonna solve gonna have perfect solution, right? No problem have a perfect solution technically. That's impossible to have. So the problem has a deviation from the expected values. That's good actually. That's not bad at all. That's good because that unexpected values, unexpected deviation are the something new is actually the providing you some new insight. Now new insight into your problem. So that actually good. That's the missing part going to be here. Any question? Okay, then let's continue. Now, all we have to do is that what we're going to do, we're going to let the simulator run. Earlier, I mentioned what information we needed, right? So we would like to have the acceleration of the object, final velocity of the object, and both of them I can find just knowing the time it took, right? So that's the idea. And also by knowing those information, I can actually check the Newton laws and also check the uh, validity of the conservation of energy in this case, okay? So all we need to do is now let this run and then extract these values. Just click on the run button on the bottom, then it will run, and then after it continue, it will show you the information about the acceleration, the velocity, and the time. Those are the information we need, right? So I need hanger mass M1, table number 1, unit kilogram. I need the height, how high M1 is started from the ground, unit meters. And I can actually calculate the velocity. I can get this number directly, or I can calculate. You will get the same number. It's not going to be changed at all. So the meter per second, let's calculate and then see what number we got, okay? And acceleration experiment, meter per second is squared. And we're going to calculate the acceleration by using mass values and the Newton second law formula, equation number 5. Meter per second is squared. And then finally, at this table, we're going to check experimentally accelerated given by the experiment and the calculated acceleration by using the masses, okay? Then our expected value going to be this calculated value. Let's check that with the acceleration given by the system, okay? All right, so what we need, the mass M1 right now is 1 kilogram, 1 kilogram. And I'm adding about few decimal places because this system can give at least 1 decimal place, but I'm going all the way to 3 decimal places, assuming the accuracy of the measured level in this class setting, okay? And the height is, I need to rerun this one. If you change anything, it's going to be reset. So just let it run. Okay, height now you can see it's negative direction it measured, right? Write it down with the negative sign because observed values we have to write it down. But that H negative sign is not interested at this point because we're going to calculate velocity and acceleration Magnitude only, okay? Because two objects, directions are different for each object, but the magnitude is same for each object, right? Because of that, I can't put any particular sign here because I'm talking about velocity finally for the both object, magnitude only, okay? Not for one particular object. H gonna be minus 2.71. And let's calculate velocity equation you got earlier. Right here, velocity is acceleration times the time, but I can do it by using acceleration is 2h time h divided by t to the power 2. So which means this is going to be 2h divided by t. That should be the velocity, right? So I can do that very easily then. Question? Okay, so this can be calculated. That is the experimental value because I'm going to use h given by the experiment. Okay, so this is going to be 2 times h. I'm going to use only positive value ABS and then divide by time given there 2.47. Okay, now the velocity I'm getting 2.194. So that's the rounded value gave here. You can see it says 2.2, right? Reason it's rounded this one, but I'm going to use this number, non-rounded value, okay? So that's how exactly, if you're doing this in class, we're going to do this calculation. H is measurable, time is measurable, but these are not directly measurable, acceleration and the velocity, okay? That I have to calculate. Let's do the acceleration experiment. Equal sign 2h, 2 times ABS parentheses h to the power h divided by t to the power 2, right? So the time is in this case 2.47 and then power 2. So I'm getting about like acceleration 0.89. I'm getting 0.888. It's a rounded value. Okay. Let's keep it like that. And let's calculate acceleration expected. This solution we done in class. That's why I did not do it purposely. But you should know how to do this solution exactly because we done at least 2 or 3 times in class this kind of questions. Okay. So this is going to be now equal sign m1 times g. M1 is the object moving vertically. In this case, M1 is this object multiplied by G 9.81. Since we in the Newton laws, then 9.81 come as just a number. The sign is automatically built into the free body diagram. Okay, divide by parentheses. M1 plus M2 is 10 kilogram. So I'm getting 0.892 and the acceleration given by the system is about 0.89 or 0.888. So it's extremely close by. That must be the case. Otherwise, the rounding errors, we should get exactly the same answer. Question. Okay, then let's percentage error between the acceleration. This is going to be percentage sign. So what we have equal sign ABS parentheses calculated value is the expected value theoretically minus this is the experimental value and then divide by calculated value multiplied by 100. So we have about like 0.3 percentage error. Any question? Okay, then let's continue. Now you can see I can actually do this one time with one particular object mass, and that is not our interest actually. What we're going to do, we're going to actually investigate by changing the mass of the object number one. We're going to actually collect a range of data. By collecting the range of data, what we're going to investigate, I can actually see whether this object number one, Newton laws, is actually behave it's supposed to be. For example, if I apply F equal ma for the object number one, horizontally, all the forces is equal mass times the ma, then you will get only force. Now, there's no friction, right? Only force is positive T, which is equal mass m2 times the acceleration. Now, what we're going to do, I'm going to calculate tension for several times later, and then we're going to put that into y-axis. Then we're going to calculate acceleration several times by changing the mass m1. Then this will give you y equal mx type graph. I'm going to use here a different symbol, maybe c. That c is the slope of the graph that should be actually equal to the cart mass. You see that? So which means if I can get a graph between the tension and the acceleration, so that graph going to be linear, by doing the trend line, you can actually investigate slope of the graph that must be equal to the mass of the cart. That we can check if I have a set of data. Okay, so that's what we're going to do here. That's why we actually repeat in this experiment with different masses on the hanger. Okay, as we have the different mass on the hanger, dragging power downward direction larger. As a result, acceleration should becomes larger. Still friction coefficient going to be 0. Okay, question. Okay, then let's continue. Right, so every time you have to reset, right? Now all we're gonna do, increase the mass m1 to maybe 2 kilogram, right? Let's increase one by one, 2 kilogram, and then just repeat this. Click on run, wait until the simulator is done. After it complete, then you can extract the values. I need the height, negative 2.61. And then the velocity I have to calculate, right? You can't click and drag here because you can see the time is actually each time changes. Because of that, I can't actually click and drag this one directly. Okay, so I have to do that calculation. So you know the calculation. Let me copy paste that function. You can use it accordingly. Function is the same, but it's going to slightly change. Okay, function for velocity, put it here. V function for v and also function for acceleration. I need the time, right? So let's copy paste that one also. A from exp. Okay, so I can actually, if you want to just type these two numbers, it's going to be very closely match. But let's do that calculation because it's going to match with exactly in class work for this experiment. All right, so let's do equal sign 2 times ABS parentheses T10 divide by t to the power 1. T is in this case now 1.79. You can see time is time needed to go the same amount of distance decreases because now you have more acceleration, right? It's moving faster now. So now it's going to be about 1.79. Now acceleration I can do the same way, equal sign 2 times ABS parentheses C10 divide by time is 1.79 and then power 2. And these two you can actually click and drag because that will do the calculation automatically. because mass M2 remaining fixed, only mass M1 changing, that I'm using these cell values, right? That too you can click and drag. You can see it exactly the same. There's no difference at all, okay? All right, then all you have to do, reset, increase the mass into 3 kilogram. Any question? And let the program run, and then that's all really we need. Only the time and h, right? Those are the numbers we needed. Mass kilogram, height is minus 2.57. Let's do this calculation then. Equal sign 2 times ABS parentheses 11 divide by the time 1.51, and then this one is 2 times ABS parentheses 11, and then divide by time to the power 2, 1.51 to the power 2, and then these two you can click and drag right hand side bottom, that solid green dot. Always check these two values, okay? A exp and then a cal, those two should be very close to each other. If you see any discrepancy there, that means we doing something wrong. There's no reason to have those two differences, okay? And that's it. Then you just continue, just reset every time, change the mass into next round value, 4 kilogram, rerun, and then extract the values 4 kilogram, negative 2.49, and then equal sign 2 times ABS parentheses C12 divide by time 1.33 equal sign 2 times parenthesis ABS parentheses C12 close brackets divide by 1.33 to the power 2, and then these two we can click and drag. If all correct, these two numbers should be exactly the same. And let's take a couple of more data points because later I like to make a graph, right? Reset it. Let's go into the next point, 5 kilogram, run the system, a 5 kilogram, and He is minus 2.46, and velocity we have to do the calculation equal sign 2 times ABS parentheses C13 divide by the time 1.23, and acceleration experimental equal 2 times ABS parentheses C13 divide by time to the power 2, 1.23 power 2. These two should be about the same, okay? If not, then something wrong. Our percentage error should be less than 1. You can see that's the one I was talking earlier. If you do this in class setting, you will never get that low percentage error. You will get fairly reasonably high percentage error. Question. Okay, just reset and then let's do one more data point. That should be good enough for our graph later. Okay, what we have 6 kilogram minus 2.42 equal sign 2 times ABS parentheses C14 divide by T is 1.15, and for acceleration equal 2 times ABS parentheses C14 divide by time 1.15 to the power 2. They are very close to each other. Percentage error is very less still. Question.
What is the formula, Professor, for acceleration calculated row, table, column?
Let's copy paste that one too. So this is a cal put here. And also this one for the percentage error. Percentage. Actually, we do in percentage error, okay, not PD. Please change that term into PE, right? There's two type of percentage errors we calculating, sometime PD, sometime PE. So we did it PE here, assuming this one is the expected one, okay? So we did PE. So we'll leave it like that actually. Since there's no standard value here, I think I was thinking to do PD, because the difference between the percentage difference and percentage error is percentage error we usually do if we have anything standard like gravitational constant or any other standard values like the density, then we know what to expect, right? But in this one, we don't have a standard value. However, we can say from the Newtonian laws, what we expecting is the acceleration, this value, right? So we can say that's the correct value. So we are comparing that to the experimental values. So nothing wrong doing that, but usually in this kind of situation, we can do percentage difference too. Question. Okay, then let's continue. Let's take a look next table then. Table number 1 we done. So in the table number 2, let's also check other any question. Under each table there are certain question we have to answer. Okay, so let's take a look part 1. Calculate the acceleration and then compare with the acceleration given in the simulator. Calculate tension and then compare into that, and then compare the tension of the system to, okay. So let's do it here now. In this case, what we're going to do, this is all calculation. Okay, the tension here, experimental value is actually given there, but we don't need that one. We can still calculate that, okay, experimental tension value. So hanger mass is the mass right here. You can just copy paste all of these numbers from the table 1. Hanger mass, tension experimental, we can calculate. How to calculate experimental tension? If you remember earlier, formula F equal ma, if I apply for the object number 2, tension is just m2 times the A. So all we have to do, calculate the tension experimentally. Let's do it this way. So this should be then equal mass m2 times acceleration you get from the experiment. That's all really, it's very simple. So I can use experimental acceleration for that one with the mass m2, right? So which means equal sign, mass m2 remaining same, 10 kilogram, doesn't change at all. Acceleration on the other hand changes experimentally. Those are the numbers on column E on table number 1. Click on cell E9, hit enter. So that's the equation I'm using to get T exp. And if you click and drag, that will give you the tension experimental values. Those are the numbers were given on the simulator, but we did not wrote it down those earlier. We could if you want to, but we can actually calculate. You can check the last one at least. So if you check the last one for 6 kilogram M1, in the simulator it tells you tension in the string 36.75. I'm getting 36.597. So it's extremely close by. There's a little bit of difference because everything here we calculated, not the given values here. Okay. Question. Tension calculated, on the other hand, is based on the Newton laws, right? So if I use the Newton law, calculated tension is actually you can do by using this equation number 4 right here. M1 M2 times G over M1 plus M2, which means, let's write it down, that formula also here, equal sign M1 M2 times G divided by parentheses M1 plus M2. That's the formula, right? I can use that directly to do this calculation. Equal sign, parentheses, M1 is this number right here because M1 changes. Because of that, it's better to call that cell value, times M2 is 10 kilogram times gravity 9.81, close brackets, divide by parentheses, M1 cell value B23 plus M2 is 10 kilogram because M2 doesn't change. Hit enter button if our prediction is correct and the simulator done the correct calculation itself. So we should get about the same values. You can see a little bit of error there. That's better because part of the game of the physics experiment is actually trying to understand the error. So that's what is missing with the simulators. But since we done the little bit of calculation values earlier for acceleration experiment, we still getting a little bit of error there. That's better to have it. So this is the function we are using for tcal. Question. Okay, let's do percentage difference, or percentage error. We can do either one actually. Earlier we done percentage error here. Let's do percentage difference here to see what's the formula look like. Okay, doesn't matter, we can do either. Since there's no standard value given, percentage error is not required to do actually. Okay, percentage error is required. PE must be done if there's a standard value, that must be done. There's no exception for the standard value. Since the standard values are not here, I can do either percentage error or different. Let's do PD here to get practice with that equation, right? The PD is slightly different, right? So the denominator going to be the average. Otherwise, the formula looks the same. Equal sign ABS, parentheses, TCal, that is the expected value, minus experimental value, you close bracket, divide by double brackets, expected value plus experimental value, close bracket, divide by 2, close bracket again, multiply by 100. Now you can see there's no big difference at all. Earlier what I got 0.384, but I did PE. Now I'm doing PD, about the same error because PD and PE both actually tells you how closer these two numbers are, right? So these two numbers are very, very close to each other. Question. Okay, then let's continue. No question? Anybody have any question? All right, so let's continue then. Okay, so where we are now, we done TCal for first hanger mass, right? All I need to do now, since I use the formula, this is very easy. Let me copy paste this function too. So I did PD for this one because I want to check how the formula changes affect to the number compared to the previous. Okay, you can see it almost has no effect. Only difference between PE and PD is the denominator is the average here, okay, between two numbers. Rest is just simple, right? You just click and drag. That will just do the calculation for you. You can see numbers. These two numbers are the ones you have to compare. Those numbers should be extremely close by each other. Let's do the percentage difference between tensions. Those numbers are very, very relevant and then close to previous numbers because previous calculated and these acceleration values are actually the deciding parameters for these two, right? Because of that, whatever difference, they are going to show up here too. That's the idea. Question? Okay, let's make a graph now. So let's make a graph between earlier. Remember, I mentioned that if I have a object number one, formula just equal m2 times at is the force. We just calculated that, right? And then m2 is the object mass on the horizontal plane. That mass m2 remaining fixed throughout the experiment. So I have a data set. Data set shows me how the force changes as a function of acceleration. Let's make a graph and then re-estimate the mass of the cart, right? So let's see whether I can get the right number. Let's make a graph. To make the graph, now you guys should be familiar of this thing, right? And you may need the one picture of the simulator here, right? So let's take one picture of the simulator that you can add somewhere into here. I'm showing this one again and again. The reason is still very few of you now. Actually, we have a group of people who know exactly what most of the time what you guys doing, but it's still very few people still shows the sign of they don't know really what they're doing. So that's still troubling. And also it unnecessary point reduction and the point loss you're getting on the labs really, because lab points are something very easy to earn. It's not anything serious at all. Follow the carefully everything what we discuss. I show everything, every single calculation what you're supposed to do. This is like a preschool work, right? So you just need to follow these steps and then complete it, and that's really troubling. I see a lot of errors in some lab report, but very few, okay? So very few, almost everybody now doing the labs very good level. So now this is going to be our figure one. This should be going to your procedure section, right? This is the simulator for Newton laws, Newton law analysis, or you can say analysis of Newton laws. That doesn't matter. Okay, you can define any way you like. Newton simulator for analysis of Newton laws. Okay, so you can define that anyway. I don't really do any point reduction or anything for those things. And then let's do graphing now. I would like to make a graph. Let's insert very top, and then in the middle there's a different option for the graph. Now we interested is scatter plot, right? Let's do a scatter plot and then double click, select data. Now if you remember earlier equation, F equal ma, tension should be on y-axis, acceleration should be on x-axis, right? Add data, x value should be acceleration. I would like to make a graph between a cal, all the numbers from f9 to f14, and then t cal is D23 to D28. Click OK. Click OK. I have one graph there. If you have a graph, all of these now you should be much familiar, right? Chart title. This is going to be what? Tension force versus acceleration. You have to name the graph, double click. Left hand side very top, chart elements, axis title, horizontal, again axis title, vertical. And also if I have a graph, I would like to have the trend line because it's a linear. Let's pick with the trend line. So this is going to be now acceleration x-axis, right? Acceleration meter per second squared. And then y-axis is going to be now tension, right? That is our force. Tension unit going to be Newton. If you have a graph and the trend line, we would like to see the trend line equation, right? Bring the cursor on top of the trend line, double click. In the right hand side, very top, third icon, click on that. Trend line options, go all the way to the bottom, click all these three. As soon as you click that, you will get an equation. That's the equation we're looking into. Right now, equation shows you only two significant, not only two, it actually one significant figure. It just said 10, which is not good. We would like to see more significant figures. But you have to bring your cursor on top of this box right here. You see around the equation, just bring it on top of the line and then double click. Then you will see a couple of new icons appear to your right hand side. Very top, there's a 4 icons, fourth one. Click on the fourth one. Then you will see number, category, general. Click on the general, change to number, and then increase the decimal places right here into 4. Then I can make sure calculated value is actually accurate, right? If I'm missing those decimals, if I have numbers there, which mean they are going to be a percentage error still, right? But you can see that number is the mass of the cart. That is exact because mass of the cart we keeping 10 kilogram, right? That exactly the number we need, right? So that mass of the card, since it is constant, you may add those numbers into the table. That will be good for you when you do the discussion. The M2 we keeping at 10.0 kilogram. You can add into very top of the table. So that is useful when you do the discussion section. Okay. M2 is about 10.0 kilogram. Question. Now that's the number exactly we expecting. We have 10.0 and R square is perfect because this graph is for the calculated, right? Now let's do the same. Any question for the graph?
Can you show
Yeah.
the number, like to extend the y to 10.00 again?
How to increase the decimal places? So you all you have to do, bring your cursor on top of this equation. And then you will see this line, right? Outer line, outer border, just bring it on top of the border, double click. As soon as you double click, this 4 icon on the very top right hand side will appear. Click on the last one, fourth one. Then you will see number, category, and then click right here. It should say generally. Then just click on there, then change into number, then change the decimal places into 4. Okay, question? Any other question? Okay, now let's see the same thing. Now we have a graph, right? But I did that for the calculated value. Then of course I should expect the perfect answer, right? Because I did the calculation by using that now. There's no need to be any difference. But however, I have these experimental values, right? CT experiment and A experiment. Let's do the same graph with that. You can make a new graph, but I would like to just add the data here. Double click this one. Double click anywhere on the graph sheet. Click on the select data. Then you see the series one already there. So we're going to add a new data set, that is a new series. Click on add. That will add a new series. So X value is going to be now A experiment is starting from E9 to E14. And then the Y value should be tension experiment is starting from C23 to C 28. Click OK, click OK again. Now you will see another data set, right? Now the two data sets are exactly on top of each other. You see that? So which means, of course, there will not be any difference at all at the end. So let us do one quick check to see whether there's any visible difference. You can make another copy of this graph. Click on the graph, go to the home, copy, and then paste it elsewhere. Then you can make a copy of the same graph. What I would like to see is that whether this is exactly same data set or there's any difference. Okay. We can just get rid of one data point here and then see whether it's exactly look alike. Yeah, I think there's no difference at all. Just you can leave it like that. So, oh, let's make a two graph. It's gonna be look not really anything meaningful because data points are on top of each other. We have to see it differently, right? If you're making it two graph, not much meaningful this way. Just get rid of that data set, double click, select data, series 2, click remove, click OK. Let's make a different graph, otherwise it's not much meaningful. Let's make another graph to see that what we're interested to see is actually the slope, right? I would like to see whether it's exactly 10 for the experimental values or slightly different, right? So I can't do it by using the same graph. Let's make another graph. It's not a big deal since you have the same graph. If you want to make a similar graph with a different data set, easiest way is that make a copy of that. Click on this graph sheet, click on the home, click on the copy button. Then click elsewhere on the Excel sheet, click on the paste. Then you can recreate the same graph. Okay, now these two graphs are exactly the same. Now what we like to do is change the data set on the graph number 2. To do that, all you have to do double click and then click on the select data right hand side very top. Then click on the series and series 1, then click edit. Now this data is actually for the previous, okay? For the previous, you have this data, okay? Just delete it. If you delete the y first, then it will not let you to do anything unless you add the y range. That's okay. Let's add here. Y range should be T experiment, starting from C23 to C28. Then go back to X and then delete everything there. X should be A experiment, starting from E9 to E14. Click OK. Click OK again. Now you have a new data set. Okay. Now this data set is actually not the previous one. This is new one for the experimental values. You can see there's no difference at all. M2 values is exactly the same. Okay, question. Since the two graphs are same, if I include these two into the report, then it looks very similar, right? So then make sure you have to rename this properly, right? So let's rename this. You can change the colors if you want to, but naming is more important than that. This is tension force versus acceleration. This is for calculated, right? You can put parentheses calculated. And this one is the same tension acceleration, but this one is actually for experiment. You can say experimental. Then we know that is two different things, not the same graph. Okay, question. So make sure you rename accordingly the graph, and you can see the M values are exactly the same, M1. So I was expecting maybe slightly different, at least third or fourth decimal level, not at all. It's very perfect. If it's slightly changed, that actually better, but that's okay. Any question? Any question? I'm just gonna repeat the trend line for this one, okay, to make sure it is actually the correct trend line and the number is accurate. Just repeating the trend line again. I still want to check whether it's 10 or 10.00 something difference or exactly the same, that's all. If you have it, just leave it like that. There's no difference. Okay, there's no difference, no effect at all. That's okay. Question? Any question? Okay, and also name the figures. Okay, actually there's no meaning creating two figures. I was expecting it to be slightly different, but it's actually not. That's okay. So let's name these two figures. This is going to be then what figure number? We're going to have one more picture here for your procedure section, because later we're going to apply friction. Okay, so let us start from figure number 3. Figure number 3 is going to be then tension versus acceleration for calculated values, right? Calculated, then it's going to be the same for this one, but for experiment, that's the only difference. It seems to be not much meaningful even doing that. That's okay, just to make sure. That's the one we're observing. Okay, question. That's the problem, because our results are too perfect, right? So that's, I was expecting, because of this percentage error, to see very at least maybe like 4 decimal place different, but nothing at all. It's that's what it is, because the simulator gives us always very perfect result, right? Nothing we can do about it. But if you do this in class, then you will get a whole different case here for the second graph. Question. Okay, then let's do mechanical energy analysis. So how to do the mechanical energy calculation now? Mechanical energy we discussed earlier. Two types, kinetic and potential, right? Now we interested to see mechanical energy when the objects are starting, which call initial point. Then the mechanical energy when the objects are reaching the final point, right? So the initial point mechanical energy is just mgh, because there's no other energy when it is starting at 0 velocity. Only object number 2 is at above the ground, right? So it's going to be just object number 1 m1 times gh. That's the potential energy. But the kinetic energy at the end, both objects are moving, m1 plus m2 times v square divided by 2. So let's do that calculation and then see what we get. Any question? All right, then this is all calculation. Hanger mass remain the same, right? Throughout, doesn't change. And just bring it directly here, copy paste from the previous. And the energy, of course, now the unit of energy. What's the unit of energy? Units of energy. Energy is what? We're going to be talking about this from chapter number 7, probably this week. The energy you can calculate by using the work done. Idea of the work done is actually the dot product between the force and the displacement vector. Okay. So that is the way, that's the right way to write it down, the work done. If you just remember from your high school or middle school level, work done is force times the distance, so the first times the displacement. That is not the correct way of writing that. Okay, no longer in this class that is actually valid. So if it's asking, you have to write it correctly because these are vectors. When you have vectors, you can't just say you multiplying two vectors. You have to specify which multiplication we are interested in. So when it comes to vector multiplication, there's two types we discuss in class, right? So chapter number 2, that's why we spend a lot of time there, because that's very important. In this case, what we're interested is actually dot product. The reason, the result, what you're actually getting here is a scalar. So that's the idea of two type of vector products. Sometimes interaction between two vectors will produce a third vector. Sometimes interaction between the two vectors will produce just a number. So this is one example of that. Interaction between these two now producing just a number. That's the energy. So in terms of unit, force is measured by meters, distance is measured by unit, force is measured by Newton, distance is measured by meters, Newton meter. That's the unit we actually usually represent by the joule. Okay, you can write it that way. Also, Newton is kilogram meter per second square times the meter. That's going to be kilogram meter square divided by second square. That also equal joule, right? We're not going to use any of these unit definitely. Sometime we may write Newton meter. That's okay, but for energy, most of the time it's a joule. Okay? So that unit you can directly use. Question. So this can be units joule. Because of that potential energy also units joule. There's no difference at all. And then let's check the percentage difference between these two, because none of them are standard or anything. What we're checking here is the validity of the conservation of energy. We're expecting these to be the same. If that is the case, percentage error should be 0, but you may get very little bit of percentage error. If you get that, that's okay. Then you have to write it down in the discussion why you observing that. We discussed earlier, I gave you a couple of points earlier in terms of fluid motion underneath the card surface, okay? And you have to write it down a little bit of information. If you see any difference here, why, okay? Question? Okay, let's finish this calculation and then take the break, okay? So let's finish this one. So what we're going to do, kinetic energy, final point, equal sign, parentheses, equal sign 0.5, 1 over 2 is half, right? 0.5 multiplied by parentheses, mass M1 plus mass M2 is constant, 10 kilogram, times V to the power 2. V you already have earlier, right? See that? We already have it. Click on the D9. Power is shift and number 6, 2. Hit enter, so it will calculate the final velocity and the it will take the final velocity and then calculate the kinetic energy final. Kinetic energy final itself, the total mechanical energy final of the whole system, because finally there's no potential energy for both objects. Question. Then all I have to do just click and drag. So that will do the calculation automatically. Let me copy paste this function. This is for the E total final, E final. And let's do the initial. Initially, we discussed earlier, both objects are at rest. Only one object above the ground has a potential energy, equal sign. M1 is the object above the ground, right? So the M1 is click on the cell B37 multiplied by G is 9.81 multiplied by H is actually, you can see it's measured downward direction, but we interested here only the number, right? So let's do ABS. Only we need absolute value of this H. H is cell value C9, close brackets, hit enter. If that correctly done, then these two numbers should be exactly the same. However, you will see very little bit difference. See that? That's where you have to explain why. So which tells you energies look like not conserved. So there may be little bit of energy loss. So that you have to explain. There are going to be definitely energy loss. You can see energy final is less than little bit energy initial. So definitely that confirm there's little bit of energy loss. So that mostly because of their friction. If you do in class, you not even getting this close. You're gonna get like maybe sometime 10% error is also a good value in class setting. Question. Okay, just click and drag, then it will do the rest of the calculation. Highlight this, and then that is gonna be the E final. E final. And then let's compare these two. That comparison will give you about the idea of the energy loss, right? Equal sign, ABS, parentheses. This comparison doesn't matter, but let's compare to the initial to final, right? Initial minus the final, close brackets, divide by parentheses, double initial plus the final, close brackets, divide by 2, close brackets again, multiply by 100. So there's a very little bit different, not much, but that difference is critical in this kind of calculation because that telling you more information than just a number. Okay, this is the PD calculation. What does it tells you is actually the validity of the validity of the conservation of energy. That's very important concept we will be starting talking about from next chapter. Just click and drag, it will do the rest of the calculation. It's about the same kind of percentage error we got for previous two tables. Okay, you can add actually information of mass M2 remaining same 10.0 kilogram onto the table because that's an information which actually we need. Okay, that I add into here and also I add into there. Question. Okay, then let's take a quick break and then we'll start in 10 minutes. So let's start that. Okay, so let's make a graph, insert, and then again the scatter plot we always doing, right? The scatter plot. Let's add the data, double click, select data, add X values. Let's put initial total energy starting from what D37 to D42. And then Y values, let's put final C37 to C42, click OK, click OK again, nice linear graph. Chart title, you can say this is E parentheses initial versus E final, and double click on the graph. If you know now these things, chart elements, left hand side very top, axis title, horizontal, axis title, vertical, and then I would like to have a trend line, right? If you have a data set, we always like to fit that. And if I have a trend line, bring the cursor on top of the trend line, right click, and then last icon on the very top right hand side, and then click all of these three, what our expectation now. slope of the graph should be about 1 if it is perfectly energy conserved situation. Now you can see it is slightly off. The data set is perfect. R square is 1. That means data set is very perfectly matched. However, the slope number in front of the x is 0.9967. They are going to be very, very slight different between the expected value and the calculated value. So we can do a percentage error there. Okay. So let's do x-axis. This is E initial and the units joule. And this should be E final then. Any question? Always raise an equation, okay? Doesn't matter anytime you would like. If you don't ask any question, I'm going to continue, okay? Since we're doing most of the time a lot of calculation with the simulation, there's no anything actually we can do, nothing much we can do in terms of experiment point of view with the simulation. That's why I included as many calculation as possible. Then you can at least gain good amount of skills you needed in terms of data analysis and things like that. Okay, that will be benefited anyway. So this is going to be our what figure number 1, 2, 3, 4, 5. This should be figure number 4. I'm going to name this as a figure number 5. Make sure you follow that figure numbers. Okay, figure number 5. This is going to be energy initial versus energy final. Okay. Now let's take a look what we have. We have a slope is about 0.9967. Let's write it down here. Slope of the graph. Slope is actually equal 0.9967. There's no units, okay, because you can see unit cancels out, but the expected value of the expected slope should be about 1, right? 1.000. So we can compare this, right? So let's compare this. That's the expected value. This is the slope value we getting. So let's do PE because we have expected value, right? Let's do PE equal sign ABS parentheses expected minus experimental close brackets divide by expected multiply by 100. So that confirm again, there's a little bit of percentage error because of this reason. You can see the reason is actually you can see with the percentage error. So that's the same idea you observing actually here. Okay. Question. Okay, then let's continue to next step.
Professor,
So
can
the
you
next
actually just
part,
show the function you put in?
PE function here. Yeah. So this should be then PE for this table which we just done. Okay. Okay, now let's continue to next part. So the last part of the experiment. So the last part of the experiment, what we're going to do, part C, mechanical energy we just done. Okay. Part C, what we're going to do, we're going to apply the friction. Okay, now you have a little bit of idea about friction. We discussed last week, right? So we're going to continue a lot of question this week too. Then what we're going to do here, let's apply the friction into horizontal plane and then recalculate everything what we just done. There's nothing new. But as soon as you apply the friction, things going to be changing. Formulas are changes. We did this kind of similar equation, similar calculation on our experiment, on our lecture class last week, I think. So let's take a look what's going to be changing. So as soon as you apply the friction, so the thing's going to be now very different. I have object here connected with the string and then other end. So this is object number 2. This is object number 1, free body diagram, M1G downward, T upward, T horizontal. As soon as friction is there, friction force gonna show up as soon as you apply a force into the object, right? So this is gonna be then M2G, this is gonna be then normal force. Then now again, what we like to know is what's the equation for tension, what's the equation for acceleration, right? You can just write it down, F equal ma for m1, horizontally y-axis, t minus m1g is equal negative m1a. For object number 2, horizontally, T minus friction force is equal M2A. Now, whenever you see friction force, now you should have these ideas, right? Friction force always is equal mu times the normal force. Normal force is equal M2G here. The reason there's no any motion on y-axis, there's no other forces either, right? So which means friction force is equal mu times the M2G. Let's plug it back. Equation number 1, T minus M1G is equal negative M1A. Equation 2, T minus mu M2G is equal M2A. Subtract these two together, one from the other, then you can get rid of T, right? Then you will get minus M1G plus mu M2G is equal, negative comes out, m1 plus m2 times a. Then I can find the equation for a, right? Negative sign should multiply this side, then this is going to be m1 minus mu m2 multiplied by the gravity divide by m1 plus m2. Now, one of the thing you have to do now, these are connected to your lecture class. That's why I'm actually spending time and showing you this calculation. You should be very good on this kind of calculation. Should be able to do within like 5 minutes or less, okay? So the reason these are important, now if you apply mu equals 0, you should be able to go back to the previous equation, right? If the mu is equal 0, acceleration going to be simply m1g over m1 plus m2. I can get the previous equation, check that out. Then you can take the same two equation and then find the equation for t, right? Acceleration is equal minus t over m1 plus g. Same acceleration is equal t over m2 minus mu g. From there, actually, you can find t, right? So just you need to equal this, bring all the t's one side. We done this similar calculation some time ago. I just doing again because I want to make sure every one of you can do this kind of calculation that's directly relevant to actually what comes next in 2 weeks, right? Exam number 2. Then bring the t's into one side. Then you will get 1 over m1 plus 1 over m2. All the g's into one side, g taking out 1 plus mu. Then take the common denominator, cross multiply, then you will get m1, m2 times gravity 1 plus mu divide by m1 plus m2. Now if you take a look this equation again, if the mu is 0, then you will get the same as the previous. If the mu is 0, then you will get t is equal m1, m2 times gravity divide by m1 plus m2. That's the equation you got earlier. So that's the idea. If you have something new, then we should be able to go back to the previous concept, okay? So that's what we have seen there. So all this now, this is not a new part of the experiment or anything, okay? You've already done the experiment almost. So the next, all we're going to do, apply the mu and then revisit this concept, that's all. What happened to the system if the mu is present, right? So how the tension and acceleration changes, and accordingly how the conservation of energy changes. Now these two are fine, right? Any question? Okay. Then now these two are fine. I can do that calculation. Then experimentally you will get the values. Same study, right? There's no big deal. And then what we like to see what will happen now to the conservation of energy, because earlier we know energy is conserved, right? Final, equal, initial, but now things will be different because whenever the object number 2 moving on the plane, there's a friction force against to that, right? Friction force against to that. As a result of that, when this guy moving there, it's gonna move about h distance. Now this friction force does a work done against the motion. If there's a force does a work done against the motion, opposite to the motion, that work done gonna be negative. So that means the friction force will actually get rid of certain amount of energy. Now you will see huge difference between the energy compared to the previous case. Now I can't compare the energies at all because initial energy may not be the final energy at all. The reason there are going to be huge energy loss in the system. If there is, these are relevant to actually what comes in this Wednesday, right? Our next chapter. If there's a force taking the energy off from the system, those are actually the force which actually we call non-conservative type forces. So the forces in general in this class is divided into conservative type forces and non-conservative type forces. Conservative force mean energy conservation is validated with that forces. The gravity, the force of gravity is such a force. Force of gravity is conservative force. It will not change the energy of the system into a different kind. And if there's a force change the energy into a different kind, how I know this is change the energy into a different kind? The friction is actually create the heat, right? If you rub your hands together, then you will feel the temperature increasing between your palm area. That because that friction between the hands create actually heat. So you rubbing the hands mean you're doing the mechanical work. Rubbing two hands, that's a mechanical work. That mechanical work is actually change your energy you put it into that rubbing into the heat. So if something like that happening, then this kind of forces are called actually non-conservative force. Those forces can change the energy into one form to another itself. Okay. Question. Okay, I mean, that's it. That's what we're going to check. We're going to check what the effect of the friction for this two behavior of this system in terms of acceleration and tension. And then last part, let's take a look again. Let's find the E initial. You know the answer for E initial, the equation. Equation doesn't change at all. Let's calculate the final. Then let's calculate the changing energy, delta E. Let's calculate E final minus E initial. Then what we expecting is actually a negative value because now we know energy loss happened during the motion as a result of friction. We should get this number as a very considerable negative value than the previous, not just like 0.1 or 2, that's going to be very large value. Then that amount we can use to calculate the friction backward and then so on if we need. But I don't think we're going to get enough time to do all of this, but we'll at least test this one. So those other calculation we're going to check in the class anyway. Question? Okay, then let's continue. So we're going to do, this is same kind of a study again, right? Now only difference is that with friction. So let's go back to the same simulator, nothing changes, reset. And I can start back again. Now with the applied friction, now you can see everything gonna change. For example, let's see, let's bring back this into 1 kilogram. Let's apply about little bit of friction, not much, okay? About maybe like about 0.14 small friction. And then let's try whether this is moving with 1 kilogram. See that as soon as you apply the friction about 0.14, very small, now this is not moving, because 1 kilogram is not enough to drag the object downward, because now you have that backward force, right? You can click on the show free body diagram, you see that force, right? You have to overcome the friction to get object is motion, right? So we can't move with 1 kilogram. 10 kilogram is definitely too high there. So one thing we can do, we can check when it can move. So all you have to do, click run, and then click reset, and then run again. Then increase the mass M1 to see when it can start the motion. If I increase mass into about like 2 kilogram, actually it can move. Yeah. So we can start maybe like 2 kilogram and then continue. I have to figure out what is the good starting point. Okay. So let's reset. Let's start this one maybe at the 3 kilogram. We just need like 6 data point. We have still enough. 3 kilogram, yeah. Then we can keep the M2 same as the 10 kilogram. We don't need to do any changes. Friction coefficient, we can apply 0.14. However, mass M1 doesn't enough M1. I have to go at least to about like 3 kilogram to start the motion of the system, okay? Question. Okay, then let's continue. Let's take a look now what will happen with the friction, right? All we have to do, this information I have to add now, right? The friction coefficient, let's add into this table. So the friction coefficient we are keeping, you need to insert that information. Friction coefficient, we are using 0.14. And then M2, I'm not changing at all. I'm going to leave it as 10 kilogram. However, as a result of friction now, M1, I cannot start from 1 kilogram. I have to start at 3 kilogram, okay? So this is kilogram, height again in unit meters, velocity meter per second, acceleration meter per second squared, acceleration again the same unit calculated from the equation, and the PD gonna be percentage error sign. That's not even needed because there's no unit for PD, right? Okay, so let's start from 1 kilogram. Correction. Let's start from 3 kilogram of M1 weight. Correction. Okay, then let's continue. 3 kilogram starting weight, friction coefficient 0.14, M2 remain the same. Let's reset and then click again. And then let's wait until it finish. And then all we need is the H is minus 2.54. And the velocity we can calculate by using the earlier way, but instead we can record directly these values, okay, since we done earlier there. So let's record that 2.48. The acceleration experimental, I'm gonna record this value directly 1.21, but the calculated I have to do by using this equation, right? I have a new formula for acceleration, this one. M1 minus mu M2 G divided by M1 plus M2. Let's add that equation here. M1 parentheses M1 minus mu times M2 parentheses gravity divided by parentheses M1 plus M2. Okay, that's the formula. You don't need to add that formula to here. I just adding it just as a reference here. Okay, because those directly in the theory section in your discussion or the table anywhere, you can actually call those equations directly. Let's do that calculation. Equal sign, parentheses, M1 is cell number B50 minus another parenthesis, mu is 0.14 multiplied by M2 is 10 kilogram. I'm keeping it, close brackets twice times 9.81 divide by parentheses, cell number B50 plus 10 kilogram, close brackets, hit enter. So if we done everything correctly and our prediction is correct, of course, our calculation earlier correct, then we should get exactly the same answers. Yeah, very close by. Okay, question. So let's add here, this is how we do in ACAL. Velocity and acceleration, I just read directly because earlier we done and then we have seen there's no big difference at all with those numbers because the simulator does the same calculation, right? That's how the simulator works, right? Internally, it does the same calculation in its program. So there's no meaning even redoing it. But earlier we done to get to make sure everything is actually properly working. Question?
The A experimental equation down as well, please.
Experimental, we are not using any equation now. We just directly use the number here. If you want to use the equation that we done earlier here on the previous table, table number 1. Okay. Any other question? Okay, then let's continue. All right, so let's continue into second part. Not the second data set on the same table. If you want to do the calculation, it's the same way, okay? There's no difference at all. Still, you can use the same idea, same concept, because now, let me show you that too. That may be something useful to see the connection. So now the object number 1 moving this way is starting here. Object number 2, box number 2, moving this direction is starting with initial velocity 0. And then finally, it's gonna gain some velocity. And then distance it traveling is h, right? So it's traveling with some acceleration a. So this is time 0. This is after some time. Still, you can actually use a linear equation which you've done on chapter number 3 and 4. Horizontal direction, if you use the same equation, same concept, right? So you're going to get final velocity equal acceleration times the time. And the displacement travel h, which is equal half times acceleration times the t square. So which means if you measure time, I can calculate all of this. That's what exactly we're doing if this is in class setting. But in class setting, we can't do with the friction this system at all because we can't actually use that air track with the friction. It's designed to work without the friction or extremely low friction, maybe like 0.01 or maybe close to that number. So that's the two equation, same two equation we used earlier. Okay. Question. Okay, then let's continue. Second one, the second data set, 4 kilogram. And all I have to do, change this into reset, change this into next value. Keep the friction same, okay, doesn't change at all. 4 kilogram. Let it run and then wait until it finish. Then you calculate the answer. Okay. Anybody have any problems, questions? Okay, height is now negative 2.49 and the final velocity is 3.01, and I'm just writing down directly that numbers. Okay, we done earlier that calculation, nothing changes. 1.82. Acceleration slowly increasing because mass increasing slowly. Acceleration calculated. You can click and drag. So then check these two numbers should be exactly the same or close to the similar values. Let's do percentage different also with accelerations, equal sign, ABS, parentheses, expected minus experimental, divide by double parentheses, expected plus experimental, close bracket, divide by 2, close bracket again, multiply by 100. And you can click and drag to do the next calculation. Question. No questions? Okay, and also if you want to do this calculation again, you can do that too, nothing wrong. So we done earlier, we can use the same equation, okay? So the acceleration going to be, let's check that too, right? 2h over t to the power 2. And the velocity going to be then a times t, that's going to be just 2h over t, right? So that's the two equation we used earlier, is still valid, right? So let's check that too. Let's check this answer. Equal sign, 2 times h, ABS, parentheses, this number, close brackets, divide by the time, 1.65. It's about the same. I think the last decimal place changes very little bit. So let's calculate acceleration. 2 equal sign, 2 times ABS, parentheses, h value, close brackets, divide by time to the power 2, 1.65 to the power 2. Oh, it's about the same. Actually, it changed a little bit last, the third decimal place. So I would think that we should calculate this instead of reading the numbers there because it's rounding. Having another extra decimal place, I think would be better. Okay, because otherwise, if I do the decimal place here without calculating, we actually assuming that is 0. But if I calculate, seems to be last third decimal place, not 0. We should do that calculation. We'll do that for rest of the data set. Question. Okay, all we have to do then reset. Let me copy paste that to function again. So this is actually, you can do V, that calculation, and then A experimental with this equation. Okay. Not needed, but it's better to do, I think. Otherwise, the third decimal place seems to be, we rounding, we not rounding even, we just putting 0, it's not really much meaningful. So because third decimal place is not showing up here at all. Right, so let's continue. Hanger mass 5 kilogram, reset 5 kilogram, click run, wait until it finish, and then height is now minus 2.44. And then velocity equal sign 2 times ABS, parentheses, height, divide by the time, 1.44. And the acceleration experimental equal 2 times ABS, parentheses, height, divide by time, 1.44, but power 2. And then these two you can just click and drag right hand side and then check these two numbers, right? Those two numbers should be extremely close by each other. But we should do the calculation. The reason the third decimal place not given in here, So because of that, if I do with the 3 decimal places they are in the table, it seems to be not any accurate at all, because I'm adding 0 without any reason I should do that calculation. Okay, let's just continue. Any question? Reset 6 kilogram, 6 kilogram, let it run. We got minus 2.36. Let's do this calculation. Equal 2 times ABS parentheses H close bracket divide by T 1.29, and then A gonna be equal 2 times ABS parentheses H close brackets divide by time to the power 2 1.29 to the power 2. And these two you can click and drag. So then check these two values, a cal and then experiment. Those two should be exactly the same. Okay. Next data point, 7 kilogram on the hanger. 7 kilogram. Click run. Wait until it complete. Negative 2.32 the height. Equal 2 times ABS parentheses H divided by the time 1.2 equal 2 times ABS parentheses the height close brackets divide by time 1.2 to the power 2. We are very close to each other, 2.2223. So let's do the PD. Let me copy paste the function for PD also. Those are the function we are using for this calculation. Okay. Okay, so let's do one more data point. Any question? 8 kilogram. Start until it done. We are on 8 kilogram, negative 2.31. Let's do the calculation of velocity. 2 times ABS parentheses height divided by the time 1.13 equal 2 times ABS parentheses height divide by time to the power 3 1.13 time to the power 2 power 2, and then check these two numbers, be very close to each other. Question. Okay, let's make one picture from this one, because the mu is different, right? So in your procedure section, I think you should add every anything differently you done, then you should add a different picture. There you can add that into somewhere here. Yeah, table number 4 is better with the friction, right? Let's add that into here. So I have a new picture here. That's gonna be okay. Now it shows the friction value, right? So that should be better now. Let's get rid of anything unnecessary, and then that's our simulator. Right, and then if you have a new picture, make sure you're naming it, but this picture should go into your procedure section. Okay, this is going to be figure 2 because of that. Figure 2, this should be now simulator for analysis of Newton laws with friction. Okay, question. Okay, we could do that earlier graphs we done again and again. I don't know whether it's anything meaningful, right? Let's check that graph very end right here to see how the graph is changing. But with these, I don't know whether it's anything useful. We can try at least one graph for experimental to see how the variation is, okay? So it's the same calculation, technically nothing new. Now the second graph, what we're going to do, we're going to analyze the force of tension, right? With friction now. So let's do that. So the mass M1 is the same. You can copy and paste. And then the tension force experimental going to be in unit Newton that I can do now. Actually, we have to take a look how those are actually changing. Now these are the equation, right? So now the friction is percent, which means if you take a look the equation number one, this one, now if I make in the graph for the object number two, right? Object number two, if I make in the graph, this is the one we're interested, this equation, tension force is equal M2 times the A plus the friction force, right? Friction force is mu m times g, that is constant, right? That is not changing throughout the motion because this is kinetic friction now plays the role. If I put this tension force by finding the experimental into y-axis, if I put acceleration into x-axis, now your equation must be changing, cx plus d. That should be the equation. Now, if you take a look at that equation, now actually it's better to look at it because your M2 should be still the slope of the graph, right? If I find the slope of the graph, I can find M2. However, by look at the y-intercept of the graph, that's going to be the y-intercept. By look at the y-intercept, I can get the idea about the friction force. Friction force is, for example, mu times the M2G. So from there, I can, if I want to, I can re-estimate the mass M2 by using even the intercept. Intercept divided by mu times the G. I can re-estimate the M2 by using two different methods. M2 must be directly equal to the slope of the graph and also should be equal to the y-intercept divided by mu G. I can do more analysis than previous, okay? The slope, the graph, the shape of the graph now different because you have a y-intercept, but it is linear still, okay? That's mean very useful. We should take a look that for at least one of them for experimental. Let's check that, okay? Let's calculate any question. Okay, then let's calculate. So the force is equal by using F equal ma. T is equal mass m2 10 times the acceleration experimental we got earlier here. And let's do that expected value to see what we're getting. If that is not correct, then I have to go back and recheck what has to be difference in this case, okay? Let's take a look what acceleration expected value, this one, the tension expected value. So tension expected value M1, M2G multiplied by 1 plus mu divided by M1 plus M2, only this part new, right? Now let's do that. Equal sign M1, which is this cell, multiply by M2 10 kilogram, multiply by 9.81, multiply by parentheses 1 plus mu, that is about 1.14, right? 1.14 divide by parentheses M1 plus M2 is 10 kilogram. So now you can see I can't just use equation F equal ma directly to do this T experimental, right? The reason, if I want to do that way, I have to have free body diagram showing like exactly the previous. So now your free body diagram is different. So I can't use that way, but I have to use exactly this equation. So we have to correct it, right? So let's correct that. So let's use this equation. This is what we're interested. You can use either actually, doesn't matter. We're interested to calculate this t, okay? You can either second one or the first one. So let's use the first equation right here. So the t should be equal m1 g minus m1a. So I can write it down m1 times g minus a, but let's do that calculation by using a experimental value. A, what we got experimentally, otherwise no meaning comparing later for the t experimental and t calculated, okay? Since we're using experimentally calculated value, we can consider t gonna be now experimental value, okay? So that's the idea. Everybody see that? Any question? So you have to readjust this calculation. Now this is going to be not just m2 times a that I can't use because free body diagram is very different. I have to use instead m1 times parentheses g minus a. However, when I do that part, I have to bring acceleration experimental value 9.81 minus experimental value. So the experimental value is right here. Question: why I have this term here, sheet? Or I click on the previous sheet. That's why. Okay, if you click in the different sheet, please make sure you check these functions again. That might reading something extra. Now I have the right answer. Okay. T calculated is just by using masses. Okay, but the experimental I use experimentally extracted acceleration. So because of that, it's still these two slightly different. Okay, let me copy paste that functions. Question: tcal, and this is texp. Okay, any question? Okay, that is very good exercises. Exercise actually, if you do everything very carefully, you can learn a lot with this experiment itself. About 4 different chapters, at least, yeah, 4 different chapters in your lecture class. Okay, chapter number 4 involves, chapter number 3 involves, chapter number 4 and 5 involves all the free body diagram, everything involves. If you look at it very deeply in terms of concept and then connection point of view, you can learn a lot. All right, so all we have to do now, just click and drag because I'm calling all the cell values. So just nothing much to do. You can just click and drag. That will do the calculation. Only thing you have to do check is actually check these two numbers. If those are close by, then all going good. If those are not close by, then there's something wrong. Then you have go back like what we done earlier. I went back and recheck why the number is different. Number is different. My equations are completely different. I can't treat it this scenario like the previous case. Okay. Question. Then let's do percentage different then. Equal ABS parentheses expected minus experimental divide by double parentheses expected plus experimental close bracket divide by 2 close bracket multiplied by 100. That's the equation we are using for right here, PD. Then let's click and drag. That will do the rest of the calculation. Any question? Okay, let's make a graph, and then remember earlier I mentioned that, right? If I make a new graph, now this graph not going to behave the same way. This graph must be different now, right? See, it has actually the intercept part. Let's do this. Right, insert a graph, insert scatter plot, and then let's add the data. Let's do this for experimental because earlier we done for both goes top of each other. That's not much meaningful. Let's do this for experimental part. Double click on the graph sheet, select data, and x values. Now I have to find x value is going to be acceleration, right? So acceleration going to be experimental on table number 4. Cell value E50 to E55. And y values is on table number 5, cell number C64 to C69. Click OK, click OK again. Now if you take a look at that graph, you should see that graph will not go 0, 0 point. That one important observation that must be there. If you go into previous graph, both of these, you remember going to the 0, 0 point. See that? That's the main difference. Okay, that must be visible immediately. And let's just reformat all of these. So what we need here, this is now it's the same thing. Now this is now tension, force of tension versus acceleration with friction, right? So you have to tell what is different now. Double click, left hand side top chart element, axis title horizontal, axis title vertical. And also I would like to have the trend line because we are now have the linear behavior of the data. X-axis is going to be acceleration and unit should be meter per second squared, and y-axis should be force of tension. Right, you can just undo that one. Just this should be force of tension. Tension force unit should be Newton. Now let's do a little bit of analysis with the graph. Now if you bring this cursor on top of the trend line somewhere, double click, you will see that extra menu bar for the trend line options. Keep the linear, and the very bottom click on the last two. Do not click the set intercept to 0 because now intercept is not 0. Don't click that. Instead, just click on the backward here and then add a value there like 1 and then extrapolate the graph backward direction. Put like maybe 1.3 and then you can pinpoint crossing point to make sure graph is actually not passing through the 0, 0 point. Those are the detailed data analysis, like we're talking about this big data and then data analytics too much now. So even you have a very small data set, you can do many things with that data set. Like we can do like hours of work with this simple experiment. We're doing like 3 hours of work with the simple experiment, even without the real experimental setup, right? So all we're doing is actually detailed data analysis. You can look at the data various ways, okay? Now we have the nice trend line, which shows it actually has a y-intercept. Y-intercept value is 13.809. Slope is 9.9304. This is now which number? Figure number 6. This is figure number 6. This is now same tension versus acceleration with friction present, okay? And let's do a couple of other any question. Okay, earlier in our theory part, I mentioned that by using the slope, I should be able to extract the mass of the cart, right? The object moving on the horizontal plane. And also, same thing I can do by using the intercept, right? Let's do the both here. Earlier we done only one for one. So let's do slope of the graph, which is equal now 9.93 is equal now 9.9304. 9304. We expecting about 10, right? So the expected, we can say mass M2 from the graph, right? From the graph, which is just simply the slope of the graph, right? So now this should be about 9.9304. And the expected one is the M2, no, or you can say known, is actually about 10 kilogram, right? 10.0 kilogram. So which means we can compare this, right? Let's do PE. PE equals sin ABS parentheses expected 10 minus from the graph 9.93 divide by the expected multiply by 100. So that is actually object mass analysis by using graph number 6. Okay. Question. And all of this has a unit. Okay, this should be unit kilogram, this is unit kilogram, this is unit kilogram, this is percentage sign. I'm making this table right here now because it wasn't included. Question. And let's do one more quick analysis. Now I can do the same actually by using the intercept, right? So let's do that also. So by using the intercept, let's do right here. Y-intercept. Y-intercept of the graph is actually equal to 13.809. 13.809. And by using that, we can actually re-estimate the mass, right? Mass of the object 2 should be d divided by d is the intercept divided by mu times the gravity. So let's do that. So the mass m2 from the intercept, from the y-intercept, which is equal, let's calculate that equal sign, intercept divide by parentheses, friction is 0.14 multiplied by 9.81. So I'm getting about the same value. So that's the idea, but those two are not the same exactly. See that because we're calculating two different methods, okay? Not exactly the same, but we're getting the very good answer. So the M2 known again is same about 10 kilograms. So I can actually compare because of that, right? 10 kilograms. So you can do the PE again. So just do the PE equal sign ABS parentheses known minus calculated divide by known multiplied by 100. And all of these, this is kilogram. Okay, after you do this calculation, that must be kilogram. This must be kilogram. This must be percentage, but y-intercept not kilogram, right? So the y-intercept is actually the value of the y-axis itself, right? So y-intercept is whenever the x is 0, value of the y-intercept directly that number. So that means that is Newton, okay? Y-intercept should be unit of force. Question. Make that table yourself there, okay? Small table. Question. So all of these calculations should go under this table, okay? Anything missing will be reason for point reduction, okay? So let's do last calculation. We have about 10 minutes, good enough. So M1, just all these values, you can copy paste this calculation you've done earlier too, right? And then the kinetic energy we measuring with units joules, potential energy we measure with unit joules, energy loss gonna be unit joules again. Now remember this table, what we're investigating is actually whether there's a considerable energy loss. That must be the case technically, because we know the friction is present. That's what we're checking, right? Kinetic energy final formula is same again, right? Equal sign 0.5 times parentheses m1 plus m2 is 10 kilogram, close brackets, v to the power 2. Velocity is on table number 4, cell number D50, okay? So cell number D50 times cell number D50 power 2. Kinetic energy, let's copy paste that command. This is kinetic energy final. And you just need to click and drag. That will do the rest of the calculation for you. You can compare those numbers to the previous values. Where's our previous values? Total energy final. Oh, difficult to compare to the previous directly, because the reason now mass M1 is actually a larger value. Okay, I can't directly compare to that one. It's not meaningful because masses are different. Especially the mass number 1 is different because of that numbers is different. I can only compare energy loss. Okay, you have to wait till that. Don't directly compare these numbers. Let's calculate the potential energy. Equal sign mass M1 multiply by 9.81 times ABS of the height. So that's on table number 4, cell number C50. Close brackets, hit enter. Now you can see the difference, right? Now that you can compare, see the difference, almost half. That's a huge difference. If you go into previous table where we done earlier energy calculation right here, you can see energy almost the same. Final energy, initial energy almost the same. Percentage difference is almost negligible. Now on the other hand, you can see energy is extremely different. You can immediately identify there are going to be huge amount of energy loss. So we can actually use that energy loss amount to actually re-investigate, for example, the friction force, how much friction force is actually acting on. And then we can do other analysis by using that. We can do another 1 hour, 2 hour analysis going forward with these numbers. Okay. Don't worry, we're going to stop in 10 minutes, okay? All right, so to do the rest of the potential energy, you can just click and drag. So that's what we expected. That's exactly what we actually observing. This is potential energy. And let's do energy loss. Energy loss is just difference between final energy minus the initial. Final energy minus the initial. I should get huge negative number, right? That's what exactly we're getting. If I'm getting large negative number, then we are good, because that's what we exactly expecting here. And click and drag, that will do the energy loss. Okay, energy loss is just this function. Okay, this is delta E, or you can just say energy loss. Energy loss. Okay, equation. Okay, then let's take a look. All of the calculation and everything. I think we completed everything. One quick check. Let's go here and then take a look whether there's other question it asking. Or we can make a graph here too. Actually, that useful. You should make a graph. Just insert scatter plot. I just need to close this Excel file and then reopen sometime on the WebEx. If there's too many application is open, it actually stop responding. Okay, just close it and then reopen. Should solve that issue. Let's take a look. I think that may be the issue because my Excel file is stop responding due to some reason. Let's check quickly. I think now it is fine. Yeah. Let me reshare that. Okay, so hopefully it's good now. Let's check again. Insert scatter plot. Yeah, now it's working good. And then now let's take a look how this graph is changing. Now remember, you have to compare this graph, okay? And then let's compare this graph to again because everything is different now. This graph also should behave differently. Double click on the graph sheet, click on the select data, add, and x values, doesn't matter what the x values, but let's put initial for x and then final for y, and from initial is D78 to D83, finally C78 to C83. Click OK, click OK again. Now you should see a graph which should not go through 0 point. That's the idea. You go back to the previous energy graph right here, E final versus E initial, you can see exactly graph crossing through 0 because there's no energy loss. Even though energy loss is there, it almost negligible previous case. Now you can see it definitely not going there. It's somewhere else is crossing here. So let's reformat this one little bit. This is going to be E final on y-axis versus E initial on x-axis, but this is with friction. Okay, you have to tell how you done that graph and other information because otherwise there's two graphs exactly similar, not meaningful in the report. Okay, double click left hand side top chart element, axis title horizontal, axis title vertical. Let's fit the data with the linear fitting, and x-axis gonna be E initial and the unit should be joule, and the y-axis should be E final and unit should be joule. And I would like to see the fitting parameter, right? Bring the cursor on top of the trend line, double click, and then on right hand side the top, the third icon, trend option, keep the linear, press the last two, click the last two, but not the intercept. Okay, intercept should not be 0. And you can extrapolate the graph backward direction. You can put like about 1 and then see whether it's really crossing the elsewhere or whether it is going through 0, right? So put that into like 2. I may have to use a large number because that number, backward number, depending on x and y values, those values are larger now, right? So I have to put maybe like 10. Yeah, maybe 100. Too much. Try like maybe 70. Too much, maybe 60. Yeah, that's better. You can try maybe 50. That's better. If you do 50, then you can see very nicely where the graph is crossing, right? So that will allow us to identify how the graph is changes. Now this is actually figure 7. This is figure 7, E initial, E final versus E initial. E final versus E initial. Because usually when you typing the name, it actually comes the y-axis first, right? So the width, friction percent. And I have to correct that on here too. This is going to be E final versus E initial. That is good, yeah. So this one should be good now. Let's take a very quick look at why the graph is changes. So now we talk about conservation of energy earlier here, right? So what we expecting is actually delta E to be 0. But this is not 0. Instead, actually, this is the work done due to what we call non-conservative forces. Non-conservative forces in this case is actually friction, okay? So which means now your delta E is actually equal to W due to friction. So delta E is actually final minus E initial, which is equal W due to friction. So that's why actually you're not going to get Y equal mx type graph. So what's the graph we're producing? E final, which is equal now E initial plus the W. If, however, you can see if you go to the graph, these are the detailed information. You can learn a lot by doing this, okay? Only if you're interested, but even if you don't interested, you have to do some work to complete the lab, right? So now you can see whereas the y-intercept is somewhere in the negative side, right? So that will directly correlate to here, because if you take a look why this becomes negative, work done due to friction is actually dot product between the friction force and the delta x, displacement travel. And of course, friction is actually opposite to the motion, right? It's not supporting to the motion. Because of that, the work done we know due to friction must be negative. So that's why the sign is negative. That's what exactly you observing here. If you extrapolate this more and more, you can put like here large number, right? Let's put 100. Then you can see it pass through the y-axis too, right? So that's a negative number. You can exactly pinpoint how much work done is totally done by using the friction force by looking at the intercept. That is about 37.481. So those are the information, right? So you can do a little bit more analysis here. Work done due to friction force, for example, you can extract should be equal to y-intercept. Y-intercept, which is actually equal that number. So this number right here, y-intercept, we will finish with this one, okay? Y-intercept, which is equal minus 37.481 joules. Why not write it down, that minus 37.481. Okay, and then you have to put the joule unit here. So that's the amount of actually energy done by the friction force. And also you can compare this one because we expecting that slope to be 1. That is exactly we getting. You can see that slope should be 1 right here. There's no number that exactly we getting, but very close to 1, not exactly 1. But that's good enough. We done in the previous one too. Instead of that, we'll include this one. So I think that should be enough for this lab. Let's stop here. If you have any question, stay in the call. Otherwise, I will see you guys on Wednesday.
Thank you, Professor.
Yep.
Thanks, Professor.